So let us now read the question. In the circuit shown, capacitors are connected to a battery with the switch S closed. The switch is now opened and the free space between the plates of the capacitor is filled with a dielectric constant 3. So in the first case, the switch was closed, and in the second case, you are opening the switch and you are filling the space in between the capacitors with a material of dielectric constant 3. Got it? Let us draw the figure. Draw the figure. We got a pair of cells here. Look at this. And this is capacitor number 1, right? Capacitor number 2, figure is given there, right? Both the capacitors are identical. This is C, this is C. And right here, I got a switch. Okay, I got a switch. Initially, the switch is closed. Switch is closed means that path stays there. Got it? Right. So draw the figure. Then what? Case number 1 is what? Both the capacitors are connected to the cell. And what kind of a combination they are in? See this? The top plate of this capacitor is connected straight to the positive of cell. Bottom plate is connected straight to the negative of the cell. Am I correct? Correct. Even for the second capacitor, top plate is connected to the positive. Bottom plate is connected to the negative. Right? Which means for both the capacitors, the top plates are connected together. Bottom plates are also connected together to the same point. So they are in a parallel combination. Am I correct? In case 1, when the switch is closed, both the capacitors are in action and both are in parallel combination. Got it? So let us find the energy. Write the equation for energy. What is the equation in the energy in the first configuration? Ui is equal to, write the equation for energy, half into Cp into V square. Energy stored in a capacitor is given by half CV square. All right. Energy stored in a capacitor is given by half CV square. But here Cp has to be taken because they are in parallel combination. Right. So let us put the value. What is the effective in parallel combination? Effective in parallel combination is Cp is equal to C1 plus C2. Got it? C1 plus C2 into V square. So what am I getting now? Half into C plus C is 2C into V square. This is the initial energy of the initial configuration. Got it? And for mathematical convenience, I'm going to call this circle as U. So that makes it what? 2 times U. This is the first energy. Got it? So energy of the initial configuration is 2 times U. Got it? And then case number 2 is about what? They're saying that the circuit is broken here. Right. The circuit is broken here. If the circuit is broken, these capacitors are to be treated separately. Why? This capacitor is still in connection with the battery, right? Whereas second capacitor is disconnected from the battery, right? Why? You see a break in the path. Am I correct? So this capacitor is a case of battery still connected, and second one is a case of battery removed, which we have just discussed now. Correct? So let us look at case capacitor number 1. Capacitor number 1. Tell me about capacitor number 1. That is what? Battery. Capacitor number 1. Battery is still connected. Battery connected. Battery connected means who must be constant? Voltage must be constant. Supply voltage must be constant. If battery still stays connected, that means voltage is constant. So voltage is constant. So while writing the equation for energy, U1F. U1F stands for what? Energy of first capacitor in the final configuration. Got it? Half into, which equation are you going to use? An equation involving V. Constant is V here, right? You must be choosing an equation that includes constant quantity. So half into, before writing C, you must say what? The new capacitance. They are saying something else here. They are filling the space in between the plates with a material, right? The space in between the plates is filled with a material of dielectric constant epsilon r. I mean 3. It is 3. So write it. Capacitance, original capacitance is given by parallel plate capacitor, epsilon 0 A by D. Okay. When you fill it with a material, it is what? Epsilon 0, epsilon r. Epsilon r is given as 3 in the question, right? Epsilon 0, epsilon r, A by D. Take these together. What is it? That is the old capacitance, right? So you get 3 times C. So the new capacitance is 3 times the old capacitance. So when you write the second configuration, you must write 3C as the capacitance, right? Into V square. Put these together. What did we call this? Half CV square? That was called U, right? Half CV square was called U. So that makes it what? There is 3U now. U1F. Equation number 2. I'm done with 2 cases. Okay. Now I have to think about capacitor number 2. Capacitor number 2. What about capacitor number 2? As far as second capacitor is concerned, look at that. Battery is removed. It is battery disconnected. You have a broken path there, right? Battery disconnected, right? Battery disconnected means you can write battery removed. Battery removed means what? Battery removed means voltage charge must be constant. Q is constant. We did it now, right? Charge is constant. When battery is removed, charge must be constant. Correct? Battery removed, charge must be constant. So write down the equation for energy of second capacitor. Which equation should be chosen? There are 3 equations. Half CV square, half QV, Q square by 2C. I am choosing Q square by 2C. Why Q square by 2C? Because constant quantity is Q. So I must choose an equation with constant quantity in it. So Q must be there, right? Q square by 2C. Now, why did I put 3C? The new capacitance value is 3 times C, right? Q square by Q into new capacitance is 3C, right? And what is Q square by 2C if you remember? Q square by 2C. Q square by 2C is old energy, right? Old energy was written half CV square, which was U. All right. So what do we get now? This is going to be like U by 3, equation number 3. Okay. Then having obtained U1F and U2F, you can find the U final, energy of the final configuration. How to get it? U1F plus U2F, right? U1F, first capacitor's final energy plus second capacitor's final energy. First capacitor's final energy is what? 3U. Second capacitor's final energy is what? U by 3. Take them together now. What do we get? 3 comes here, no? 9U plus U by 3. That's going to give you 10U by 3, equation number 4. So I got the total energy in the initial configuration, total energy in the final configuration. Now I must find the ratio. That is what the question is, right? So finally you can write U1, UI divided by UF. What was UI as per equation number 1? Can you check it out? That was 3U, right? 2U, right? Okay, fine. So that was 2U divided by, what is the energy of the final configuration? 10U divided by 3. U and U are cut. 3 goes to numerator. 6 by 10 is equal to 3 by 5. Finally, you get 3 by 5 as the ratio. Got it? You can write a shortcut. Now, in subjective questions, you can use this shortcut to check if your answer is correct or not. Okay, if it is MCQ, you can use this directly to get the answer. It's a typical question. It will be asked as such. UI to UF ratio is given by 2K by K square plus 1. K is another letter used for epsilon R, dielectric constant. In this question, K value is 3 They say that in the question. Divided by this is 3 square plus 1. So that's going to give you 6 by 9 plus 1, 10. 6 by 10 is 3 by 5. That is what we got here. Understood this, all of you?